Good day. This lesson is about calculus of vector fields, focusing on gradient vector fields. Here are the objectives of this lesson. At the end of this lesson, you are expected to define a gradient vector field and sketch a gradient vector field from a given equation. Let us know gradient vector fields from its definition. It says here, given a function z equals f of xy, its gradient is del f equals, you have the partial derivative of the function f with respect to x and partial derivative of the function f with respect to y, and close in angle bracket. This is called a gradient vector field or just gradient field. It is also called a conservative vector field. In such a case, the vector field is written as f of xy equals del f equals f sub x, f sub y, and closing bracket. Gradient vector fields have an interesting visual property, that is, the vectors in the vector field lie orthogonal to the contours of f. Let us have this example. It says here, given the function f of xy equals 1/2 x squared plus 1/2 y squared, find f of xy equals del f and sketch its along with the contour map of f. So first thing to do is to define the vector field. And that is, we have it as f is equal to, or rather f of xy is equal to del f, where we have the formula, we have partial derivative of the function with respect to x, then partial derivative of the function with respect to y as its component. So in here, let's get the partial derivative of the function with respect to x as the first component, then with respect to y as the second component. So let's get the partial derivative of the function with respect to x first. So holding y as constant, so the derivative is, we have it as 1/2, copy the constant, and the derivative of x squared is 2x. Then for the second term, since y is constant, this will be 0. Then for the second component, we're going to get the partial derivative of the function f of xy with respect to y. So having x as constant now. So getting the derivative of 1/2 x squared, this is constant, so it is 0. Then you have the 1/2 y squared, the derivative is, you have copy 1/2, then the derivative of y squared is 2y. Okay, sorry for that technical error. So again, the derivative of y squared is 2y. So we write here as, again, sorry for that. So the derivative is 2y. So simplifying, we have this as, so this will cancel. So this will leave us x. Then this will also cancel. This will leave us y. So this is the del f, or the gradient f, of your vector field, which is again 1/2 x squared plus 1/2 y squared. Then let us get now the contours of the given function. If you recall about contours, these are sets of level curves. So this is in Math 147. So what we will do is to set f of xy equals z. or you can also use k. So in this case, let us use z. And this is now equal to, we have it as 1/2 x squared plus y squared. So that with this, we can now assign value for z or k. So let us just also write this as k. So that when we assign now k value, let's say we have it at k value equals 0. So this will be 0 equals 1/2 x squared plus 1/2. By the way, this should be 1/2 y squared. So this is a point circle whose radius is equal to 0. When k equals 1, so we have here as 1 equals 1/2 x squared plus 1/2 y squared. So this is now a circle with radius equal to, we have it as square root of 2. And how is this obtained? So we're going to multiply both sides by 2. So r squared equals 2 and r equals square root of 2. Okay, so I'll write here, the radius here is 0. When k equals 2 now, this will now be equal to 2 equals 1/2 x squared plus 1/2 y squared. And with that, this is again a circle. This time, the radius is equal to 4, or rather 2. Why? Because we're going to multiply both sides by 2. So this will be equal to 4 equals x squared plus y squared. And r squared equals 4, and finding r, that is equal to 2. So we will stop from here. So because we know already that we have here circles as the level curves. So when we talk about contour now, it is set of level curves. So let us draw now the contour map of your function f. So this is your x and y axis. So let's have the radius equals 0. So it's a point circle. When the radius is equal to square root of 2, that is 1.4 something. So let's just have this as our square root of 2 radius. So I plot this value of radius from the center measuring square root of 2 on the x, on the y axis also. So we now have the graph of a circle. Then let us plot also the third circle when radius equals 2. So let's say this is now your radius equals 2. So plot or connect those points now. Okay. So we may continue to draw circle. So let us just assume that this is now the radius. So no need to scale properly since we're just going to show the contour map of your function f of xy. And then what we will do is to get now, or draw now rather, the vectors that are orthogonal to the contours of f. So what will be the component of your vector that is orthogonal to the function f of xy. So the vectors that can be formed is based from the vector field or the gradient field. So we have found that the gradient field or gradient vector field specifically has this component xy. So if we are to prepare table values of xy, let's say we have it as so this is your table values of xy, and then you have the corresponding vector component of your vector field. So if I will choose 1, 1, the component of your vector field is also 1, 1. If I have a point, let's say 1, 2, then this will also have 1, 2. If I have the point, which is, let's say, at 1, negative 1, then you also have here the vector component as 1, negative 1. If you have negative 1, then you will have the component negative 1, negative 1. If you have, let's say, negative 1, 1, then you have negative 1, 1. So let us plot these vectors in the contour map of your function f of xy. So what we will have here now, so at 1, 1, let's say this is your 1, 1, because a while ago this is square root of 2, so 1, 1. So at 1, 1, so you have 1 and then 1, because that's based as the component of your vector. So let us just have approximately this point, and let's connect them. And then draw the vector field. Then let's have 1, negative 1. 1, negative 1 is located in the fourth quadrant. So you have 1, negative 1. So this is your point. Then 1, negative 1 is the component of your vector. So we measure 1, then negative 1. So 1 to the right, 1 downward. Then we have negative 1, negative 1. So it is right here. Then we will measure negative 1 as the components of your vector. So to the left, and then downward. Then we have negative 1, 1. So suppose this is negative 1, 1. Then we also have negative 1, 1. So to the left, negative 1, then upward 1 unit. So this will continue if we're going to assign another set of points here and then solving for the component of your gradient vector field. So we can just simply assume that this will be the result of your vectors that are orthogonal to the contour map. So we can just draw additional vectors here in the same direction as your vector here. So this is in the first quadrant. So they have the same direction. Likewise, in the second quadrant, we can just assume that this is the direction of the other vectors. So take note that the vectors here are orthogonal or perpendicular to the contour map or level curves. So by the way, the length of these other vectors is increasing because as we are to assign values of your points, so we have also its corresponding components. So this is how we graph this given function f of xy equals 1 half x squared plus 1 half y squared. And by the way, the given function here, f of xy, is equal to 1 half x squared plus 1 half y squared, where we can assign f of xy to be z. So this is a surface, which is specifically a paraboloid, and it is opening upward. Please remember the graph of a paraboloid, and the vertex of this paraboloid is at 0, 0, 0. Again, it is opening upward. So this is just merely the contour map of a paraboloid. So it will look like this. So this is into, or it is drawn in two-dimensional plane or in XY plane. I have here another solution of this problem. So as you can see, it says here, the vector field is f of xy equals del f, or gradient f equals, you have the partial derivative of the function with respect to x, partial derivative of the function with respect to y as its component, which is equal to xy. So it is the same way as what I have found a while ago. Then the contours of f are concentric circles of the form 1 of x squared plus 1 of y squared equals k, centered at the origin, which is also my solution or my analysis. Then we have here the surface being a paraboloid with its vertex at 0, 0, 0 and opening upward. And take note that the vectors in F, which is the vector field, or specifically the gradient vector field, are orthogonal to the contours of F, as you can see in the graph. So we have here the vectors defined by the components of your vector field, which is xy. So these vector fields are orthogonal to the contours of F. The vectors point in the direction of increasing z.